So let me just talk about definite integral. So it's just like applying limits to our reduction problem. So I'll take a particular case scenario. This scenario can
Don't they record?
yes, I'm recording. My white marker is not coming up. Let me use another one. This is not good. My whiteboard is not coming up.
You go like restart that system.
Probably I just start now. Let me start the Teams. Let me try and start the Teams.
If you restart, you go offline. Yeah?
No, you still be on the call. I'll just have to.
Oh yeah, no, yeah.
Let me see whether this is going to come up now. Hopefully, it should come up. This is looking like this. So
I'm not seeing your screen yet.
okay, you can't see it. Oh wow. Hold on. Okay. Um, okay. This. Over. This is backward. This thing is not problem, but then we shall use word. This one not that one. So Tayo, you have to create your there's a background noise at
Huh?
there's a background noise at
I can't hear you.
there's background noise at
From my end, Abby.
so
Is it from my end?
yes, yes.
How about now?
It's better now. Obtain the formula for say let me see. It's not coming up. So to obtain the formula for what am I writing here? Scroll down, scroll down, scroll down, scroll down, scroll down, scroll down, scroll down. Okay. Formula for I'm going to do an insert equation. See, I'll call it subscript n, which is the definite integral of let's say this. So I have over 2 here, I have 0 here. So let me just put 5. Okay, now find the symbol for 5. You have to do this too. So let me just go to symbol. Let me see that I have 5. Yeah. 5 over 2 of course x. And hence, evaluate hence evaluate this integral.
I don't see anything where you type.
You can't see anything. I'm showing my screen.
I'm only seeing square. I'm only seeing square the results. Can you call x squared plus 6x plus 9 close bracket minus 9 plus 13. Okay, I've seen it now.
Is a net of this. So let's evaluate this. So let's evaluate. I'm going to put 0, 1. And then this, I'm going to put equation. So here, so power. Okay. X minus 1 minus x. 1 minus x all is passing. All about x. I have this problem to solve. This is the problem we want to solve. Evaluation solving problem. So we are given this. We are told to obtain a formula for this. So this is integral of course mx dx from just power 2, and hence evaluate this. Have you guys been taught what is formula before?
Yeah?
Have you guys been taught what is formula before? What is formula?
The network is really bad.
Have you been taught Wallis formula before? Wallis formula.
Yes.
Okay, this is going to lead to Wallis formula, but let's see how it goes. So I'm just going to do a recall that I don't necessarily have to prove this. Recall that Cn, the reduction formula, recall that the reduction formula for this reduction formula, I don't think so. So reduction formula for Cn because I don't want to have it to prove this again because it's going to be stressful. So is equals to what's going to be again? Hold on.
Reduction formula for cos.
Yes.
That's 1 over. That's cos n cos raised to power cos x raised to power n minus 1 all over n sin x plus n minus 1 all over n, then cos x raised to power n minus 2.
Okay. So you have something like 1 over n. And you have this to follow. So n minus 1. X maybe sin x. Yeah, I think minus Let's see. See. So Cn is this. The global formula for cos is this. So let me just verify whether I'm doing the right thing here. Let's see. Let's look at the image. Things you see was the stress. Oh. Okay. Concern another place here. I think n minus 1 over n is there. Okay. Okay, so moving on. So there will be, wait, let me see again. Okay, plus, yes. So this is going to be plus. So plus. Then I'm going to insert n minus 1 over n. So this give us the reduction formula for say cos. But nevertheless, don't forget that this one has what boundaries, which ranges from 0 to pi over 2. Now, if I have boundaries,
Since the reception is very slow, I'm not seeing it.
can you see the screen now?
I'm only seeing 1 over n cos n x. That's the only thing I'm seeing since.
Okay, it's going to go to the screen. So don't forget that we're going to take boundaries. We're going to take this integral as boundaries. So for this part, we're going to take limits as for x when x is 0 and when x is 5 over 2. Can you see my screen proper now?
Yeah, I can.
So if I should take the limit for this part, I'm going to have a 0. So I'm going to add a 0. So I'm taking then Cn comes now because by take limits when x is pi over 2, if I put x to be pi over 2 here, cos pi over 2 is cos 90 and cos 90 is 0. So that becomes 0 minus, now when x is 0, sin 0 is 0. So whatever all this, whatever cos 0 gives me doesn't matter because sin 0 is 0. If 0 must multiply this, I have 0. So everything returns to 0. Then I'll just have this left-hand part of my equation. So it means that I'm going to have n to be equals to this guy. Are you with me? Are you with me?
I'm not even see your screen again. Hold up, let me go get let me check. It's like the network is actually bad. Let me go outside.
Can you see my screen proper now?
Hold on, hold on. Hold on now. Okay, I'm with you now. Your screen don't go again.
Can you see it proper now? Can you see it now?
Not yet, not yet.
When you're able to see the screen. I think someone is. Can you see my screen now? Can you see my screen now?
No. I think it should be from your end. Check your connection. Like, check the screen again.
I don't think this is the network. So I'll stop sharing and then I'll share again. So I'll stop sharing and I'm about to share again. And I'm sharing my desktop. Okay, so tell me when you see my screen now. So can you see my screen now?
Let's see.
I don't really know why you're not seeing my screen.
I'm wondering why.
So this is really difficult. So let me just continue. So since I'm recording it, you should be able to let me follow the recording later because.
Okay, instead of wasting time, right?
So if you are able to catch up, I'll just go over it again. So that we have Cn minus 2 to be after substituted above here. Just tell me anytime your screen should come up. So we have Cn minus 2 to now be, and just copy this. So putting n minus 2 to be n here. Putting n minus 2 to be n here, I will have Cn minus 2 to be equals to n minus 3. This one becomes n minus 2 This one becomes Cn minus 5. Cn minus 4 rather. So continuing this process. Now also to get say Cn minus 4, Cn minus 4, we can substitute n equals n minus 4 in equation 1 above. So that we have Cn minus 4 to be Cn minus 4 let's copy this and paste Cn minus 4 is equals to n minus 5 over n minus 4, then Cn minus 6. This process is going to continue and continue. Now, so it means, now when do we stop? When do we stop? Now let's take cases. Now let's consider before we even do that. So if I want to substitute, if I substitute this, let me call this first of all. And let me call this equation 3. Now, if I substitute equation 3 into equation 2, I will have substituting 2 in then Cn minus 2 will become what? Then Cn minus 2 becomes so let me copy this, put this inside the bracket. N minus 3 times n minus 5. N minus 2 times n minus 5. N minus 2. Also, Cn minus 2 as it is displayed here. One above, that's equation 1. Now Cn to become Cn becomes this. N times n minus 2 times n minus 5. then n times n minus 2 times n minus 4, Cn minus 4. Now, this keeps going on and on and on and on and on. Without stopping. So we're going to come to a conclusion. But before we come to a conclusion, we're going to find the formula for this. Don't forget. So let's consider cases, because when is this going to stop? So suppose, so we're going to assume, suppose n is odd, n is an odd number. Then it gets to a point whereby, this keeps increasing, n minus 1, n minus 3, n minus 5, and the next term is going to be n minus 7, and this one is going to be n minus 6, then you are going to have Cn minus 6. So suppose n is odd. Suppose n is odd. Then it gets to a point. K, whereby n minus k will be 1. Get to a point k whereby n minus k is going to be 1, because I'm trying to get to that point. Don't forget that k is less than 1, obviously. So, because why is this going to be 1? Because if n is odd, let's say n is 21, you can see that this sequence is reducing by even numbers. So if n is odd, it will get to a point whereby we have 21. So if n is odd, let's say 21, it gets to a point where we have 21 minus 20. So you're going to have 1. Then obviously you can write Cn as this. So say then Cn can be written as, let's say, then Cn can be written as so Cn can be written as this, then this is going to continue dot dot dot. Also this is going to continue dot 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 till I get to Cn minus k, which is C1 in this case. So which is C1. Till I get to C1. This is going to continue to get to C1. Now, let's take another case study. So now suppose n is even now. Suppose n is even. Then it gets by still is equal to 0. Because, for example, now, since this sequence is reducing by even number, there's a point where you get to 20 minus 20, which is going to be 0. So at that point, you're going to stop. So this scenario, Cn, then Cn can be written as, Cn can be written as Cn is equal to n minus 1, n minus 3, n minus 5, dot dot dot, n times n minus 2 times n minus 4. So we get to C0. So we get to C0. So now, how do we evaluate C1 and C0? How do we evaluate C1 and C0? How do we evaluate C1 and C0? C0 for both cases. For both cases. The base problem. So the base problem is saying that Cn is this. The base problem is Cn is this. So let's put it down here. So if Cn is this, what's going to be C1? You have to substitute n to be 1 here. So you can just say n is this, then we just be substituting n to be 1, then this is going to be cos x instead of cos nx. Now we are getting somewhere. So if I integrate cos x, I do get sin x as the answer. So in this case, I'll say C1 is equals to sin x next. But don't forget, we're going to take limits. Let me see, from 0 to about 2. You're going to take limits. Just look for a bar I can use to do that. Okay. I can't find so if integral of sin x and cos x is sin x, but I have to take limits. So I have to take limits. So I'll say okay.
That's what you see visually.
See the reflection of the sky. So that will give us taking limits as x tends to pi over 2. Taking limit as x tends to pi over 2 of sin x minus, so let me change this to x, minus taking limit as x tends to as x tends to 0 of sin x. So here, sorry. If x to the power over 2 sin 90 is 1. This one is going to be 1 minus, and I put x to the 0. And when I put x to the 0, you have sin 0 to the 0, which is equal to 1. So it means you have evaluated our C1 to be 1. Now, how about our C0? So our C0. So how about our C0? So what's our C0 again? We can do it like this. So going back to the question again, since Cn is this, what is C0? So it means when n is 0, if I put n to 0 here, cos x equals 0 is 1. So I'll just have I'll say then 0 integral of x from z to the power 2. So this is going to give us that C naught is equals to is equals to the limit of, because if I integrate dx, I have x. So the limit of x as x tends to the power 2 and the limit of x as x tends to 0. So here we'll say our C naught is equals to all the limit of x as x tends to the power 2 is still power 2. So just substitute x to the power 2. We still have our power 2. Power 2 minus substituting x as 0 here, you have 0. So power 2 minus 0. That will give us power 2. So our C naught is power 2, while our C1 is 1. So we can now conclude that our Cn is equals to this times 1 with our C1 in this case is 1. So n is equals to this times pi over 2 pi over 2 when n is even. So we are able to generalize for our Cn problem. First of all, obtain the formula for Cn, which has different values for different cases. So we are able to generalize the formula for Cn, case when n is odd and case when n is even. Now we are taught to evaluate this. Now to evaluate this, now if you look at this guy now and this guy, they don't actually look alike. They don't look alike. So they don't look alike. So how do I now write this guy to like look at this? How do I write this guy to look like something like this? I think I can do something like that. So now, once I evaluate this thing, first of all, let me write this. Then I write this. Can you compare our Cn? Can I see my screen now? But we won't evaluate this.
Yes. Unless
You can't see my screen. I want to evaluate this. So this is not like this.
Reception.
Timothy, what's wrong? What are you saying? Are you saying something? So, how do you solve this problem? The problem is, first of all, we'll be able to generate a formula for Cn. Now, we are now told to solve this problem. So, if you are given a problem like this, that you are told to obtain a formula for this and hence evaluate this, it means the solution to this is going to come from what you derive from this. So, it's going to follow the formula generated from this guy. So, first of all, if you enter the formula down, how can we rewrite this one to look like this? That's the problem we have now. So I have an idea in mind. So we are going to transform x to become a tree function. So I'm going to make substitution. So let's. Oh, why did you choose that? Why did you? So let's to sin squared x. Let x. So I'll not say sin squared x so that you don't confuse. So let's say x equals to sin squared y. So not let x equal to sin squared y. And the reason why I use sin is because that if I put sin squared y here now, 1 minus sin squared y is going to lead us to cos squared y because I want to have something cos. And if I should put sin squared y here, by the time I take the square root, the reason I use sin squared is because I can easily find 1 minus sin squared y. I can easily find the square root of sin squared y. And I know that something is going to happen. Something is going to happen. So if I say x is equal to sin squared y, now I want to transform this. So I need dx. So for me to get dx, I need to differentiate this. So I can say dx is going to the next one. It's going to be, if I differentiate sin square y, I'm going to have 2 sin y plus y. So in this case, I'm going to have 2 sin y plus y. Then put dy, because I'm differentiating against y. So I'm going to have 2 sin y plus y dy. Okay. Now I have to substitute inside here now. So I have dx to be this already. I have x to be sin square y, I can put inside this. Now, so this limit is for x, but I'm transforming from x to y now. So I have to transform the limits. So I will say when x equals to 0, so when x is equal to 0, say for example, then you are saying that 0. You are saying that 0 is equal to. So you are saying that 0 is equal to sin square y. 0 is equal to sin square y. So if you are saying this, definitely you are saying that sin y is equal to 0 because if you take square root of both sides, it's 0. So you are saying sin y. So if you say sin y is equal to 0, what's y? Y is 0. Then because y is going to be arc sin 0, which is actually 0. So y n plus y is equal to 0. So you have found the lower limit for y. When x is 0, y is 0. Now, all about when x is 1 for the other comparison. You have done for the lower limit 0 down when x is 1. So when x is 1, then we are saying that 1 is equal to sin square y. We are saying 1 is equal to sin square y. If I say 1 is equal to sin square y, then I'm saying 1 is equal to sin y. Take square root of 1 is still 1. So forget about maybe positive or 1 anymore. Let's just neglect that for now. If you are saying this, what's y then? Y is going to be arc sin 1. So what value of y is sin y giving us 1? That was 90. Because sin 90 is 1. And what's 90 milligradients pi over 2? And in this case, we are saying y is equal to pi over 2. And we are getting to what's our question back. So our lower limit is 0 now, our upper limit is y now, is pi over 2 now. Then let me just copy this. Or first of all, copy this. Yes. Copy this. And say this is now equal to copy this. This is now equal to integral from z power over 2 of, so let me copy this 1 here, then instead of into 1 minus x. Now our lower and upper parameters change from 0 to 1 to 0 to over 2 because when x is 0, y is 0. When x is 0, y is 0. When x is 1, y is pi over 2. When x is 1, y is pi over 2. So 1 minus x, what's my x sin square y? So I remove this and put sin square y. Then square root of x, what's my x sin square y again? Then I'll replace dx with this. So remove dx and replace it with this. So, okay, that's brilliant. So moving on. So here, forget. And just see, it's going to give us 1 minus sin square y is cos squared y. So I'll just replace this with cos squared y. Cos squared y. 1 minus sin squared y is cos squared y. So I'll move this. Cos squared y. Then square root of sin squared y is sin y. Okay, good. So I'll move this. I'll replace with sin y. The square root of sin squared y is sin y. Then, okay, this follows. Then don't forget, sin y becomes sin y here. Good. So we can proceed to the next line. Then these two can come outside. Since it's a constant, I remove this from here. Sin y already cancelled sin y here. I'll delete it. Or still leave it like this. Okay, let me just delete it. Now, cos squared y raised power 3. This power is just multiply each other. That will be cos raised power 6y. So, let me copy this. This is here. So this becomes cos raised power 6y. Then don't forget sin y has cancelled sin y. So I'll move this. I have cos 6 power 6y times cos y dy. This cancels this. 2 comes outside as this. Cos square y is power 3 is cos 6 power 6y. And this cos y is cos y, this dy is this dy. Alright. Then we will happen next. Cos 6 power 6y times cos y, that's cos 6 power 7y. Then this gets deleted. We have cos 6 power 7y. Okay, now comparing, so let me call this. Let me call this one our which equation do I stop that time? I stopped at equation 3. So let me call this equation 4. So, comparing 4, this with this now. Let's question 4. I'll just say C7. So comparing this with this. Where is it again? This. So C7 is just what we have there. So I'll just say this is and C7. If equation 4 here is Cn, if I put 7 here as n, then I have C7 expressed here. So this 2 is this 2 here, and this integral becomes C7. So I can now evaluate C7. Now, 7 is odd. So we'll be using this formula. Cn is equal to this when n is odd. So by using this formula, C7, since n is this, and so by using this. So our C7 will now be, that C7 will be 7 minus 1, 7 minus 3, 7 minus 5. We're going to stop at 7 minus 5. We cannot get to 7 minus 7. So because it's left with 0, that doesn't make any sense. So stop and this will stop at 3 of these 2. So this is going to be 7 times 7 minus 2, 7 minus 4. After 3 of this up here, you stop at 3 of this here too. But if you put 7 minus 6, it doesn't count. Because 1, it doesn't change anything. So, then we say C7 equals to 6 times 6 times 4 times 2, and here we have 7 times 5 times 3 times 1. So that your C7 becomes equal to, so 4, this times 4, 24, 24 times 2, 20, 48, divided by 7 times 5, 35, this after is 3, 1, and 5, 48 over 1. This one is multiplied by 1 is 48 over 1 and 5. So this gives, this is our problem. This is our problem. So this really makes a lot of sense. You can really do this. I believe you can. It's going to make a lot of sense to you. You can really get the intuition behind this. It's very simple. It's nothing difficult. We are not done. Don't forget, our problem is 267. So answer is actually 267 plus 2 times 48 over 100. That's what it's about 100. So this gives us 96 over 100. Our problem. So this integral, where is it again? The answer to this integral is 96 over 100. You can use your scientific calculator, which is get the same as this. So again, so I would like us to try this out. I'm going to enter another thing entirely next week. So I'd like us to try this out on our own. I'm going to send this slide to us. This I'm going to send a slide to us that even the solution can go through it. We'll still try it at the end. So that is the slide I will be sending to you will include this solution. But first, try it on your own before looking at the solution. Practice question. I'm going to be using IAU. If math is n is equal to this to square x is sine is by nx cos square x dx. Where n is greater or equal to 2, and symbol n is greater or equal to 2. You have to prove that In is equal to, let me quickly go to this. Yes, please. Prove that In n minus 1 over n plus 2 times In minus 2. Sorry? Times In minus 2. Then hence, evaluate integral minus 2. Let's evaluate Let's evaluate science. This for 5 days. This. Evaluate over 1 plus times per x. So let's see. Over 1. Over 1 plus times per x. Raised to plus. So hence evaluate this. So we are going to evaluate this. If in is this, n is greater than to prove that in is equal to this, hence evaluate this. So that will be all for today. I would like you guys to practice this and can look up the solution later. I'll send this to you. Then I'll send this solution I have between them. Where is this step? Send the pictures. Okay. So I'll send it to them. Thank you.